Hello everyone, welcome. Today we are going to learn about set theory, and specifically injectivity, surjectivity, and bijectivity. If you don't know what these words mean, that's perfectly fine. After the end of this video, you guys will have a well-understood notion of what these words mean. So let's start. First of all, what is set theory? Well, set theory is just the study of sets. And that brings the question, what is a set? Well, a set is just a collection of objects. In the same colloquial sense of sets, that's the set we mean in set theory. Just a collection of objects. And some set theories, like CFC set theory, there's a bit more nuance to it. But for a first course in set theory, a set is just a collection of objects, and that's it. So, for example, I can have a set of apples. I got a red apple, a green apple, and another red apple. That's a set of apples. It's a collection of objects. That's it. I could have a set of bananas, right? They don't have to be fruits, but you can have a set of bananas. Maybe have like a spoiled banana here. This is the set of bananas. The alphabet is just a set of letters, right? I have A, B, C, D, E, F, G, and so on. A set is just a collection of objects. I could even have a set of numbers, like the real numbers, or just the set of numbers like 1, 2, 3, fractions, decimals, all that cool stuff. So, in set theory, we usually denote sets with these brackets around them. So if I have like this bracket, and I have this red apple, this another red apple, and a green apple, that would be that would be a set. So this is a set already, right? But to denote a set, we would put these brackets around it and put commas between the elements of the set, just to make it clear that we are talking about a set. So it's just a set of apples, but to make it more clear that we're talking about a set of apples in some context, we'd put brackets around it. Now, each of these apples are said to be a member/element of the set. And we usually name sets with some letter. Let's call this the set of apples. Let's call that A. So I took these set of apples, just put some brackets around them. You don't have to. It's convention, but we usually do. Then we put commas, and then we just label this whole thing A, and that's our set. Now, similarly, I may make a set called B, and make that the set of these bananas. Then have like a brown, disgusting banana. And I put commas around it. And each banana is said to be a member of the set of bananas, which is just B, right? Now let's go over some set operations. So we're not going to talk about operations that act on elements of a set. That's what's covered in group theory. In set theory, we only care about operations that act on the sets themselves, really. Not so much the elements of the set. So we're not going to change the elements of any set. We're just going to change sets themselves. Let's talk about what unions are. So the union of A, the set of apples, and B, the set of bananas, is just going to be, this. You probably already see what a union is. This is the union of the set of apples and then the set of bananas. So what a union is you just take the elements of one set on the elements of the other set and just stick them together into one big old set. this is what the union is. You just take elements and these elements, put them like all together. So here we have these sets of apples and bananas. Now we're not adding these sets. If to add a set, that would be like using an operation. These are unions of sets. Now what about intersections of sets? Well, the intersection of two sets are just the elements that these sets have in common. Okay, so let's say I have sets. I don't know. Set M has elements A, B, and C. Okay, and set N has. Let me put it here. Set N has elements, maybe, I don't know, C, D, and E. The intersection between M and N would just be C, because it's just the elements that they have in common, which is C. If M was A, B, C, and D, and N was, say, C, D, and E, then the union of them, the intersection of them would be C and D, just the elements that they share in common. Now, we usually write set diagrams in set theory. So here I could say it's like set. I can say it's set M, and here I can say is set N. And on all the points in M, you know what? Let me just use A and B instead. Let's just use A and B instead. So here I have set A, and here I have set B, and all the points in A represent the elements of A. Same with B. Okay. So the union of A and B, would just look like this. Oops, my Apple Pencil has just died. Just wait like 2 seconds. 1, 2. So the union would look something like this. You just take these guys and combine them to one big little set. Here's the union. And the intersection of A and B would just be what's shared, what's in between. So the intersection, would look like this oval kind of thing. So we usually use these diagrams to kind of picture sets and in their operations. So far we've talked about okay, he just died again. But so far we've talked about a couple of things. We've talked about what a set is, or what set theory is. We've learned what a set is, and we've learned some set operations. Now let's talk about functions on sets. Now I'm going to assume that you guys already know what a function is. It's just a mapping, pretty much. So a function, actually, let me not assume that you know what it is. A function on a set is just a mapping of elements of one set to elements of the other set. So here's an example. Say I have set A, and here I have set B. And here I have some of the elements of A. And I have some of the elements of B. A function would take elements of A and map it, well, a function that acts on set A and maps it to set B, will act on an element of A and map it or assign it to one point of B. Here's an example of some function f. It just takes some elements of A and map it to some elements of B. It doesn't have to map it to all elements of B. It doesn't have to take all elements of A. But a function will just take some elements of A, could be all, but in general, some elements of A and assign it an element of B. Okay? And we call a function a mapping sometimes. Now, let's talk about injective functions. An injective function. Now, the difference of an injective function is just a function that if a function acts on, say, xn, and it equals f of xm, that would imply that xn equals xm. That's what it means. Now, this may seem abstract, but I'm going to show you what the physical depiction really means. So again, let's go back to this function here. Let's erase some things to make it a bit more simpler. Now here, I might have some function that looks like just like this, okay? This function, there is a unique 1-to-1 correspondence between elements of A and elements of B where the function is defined. And sometimes we call this the domain, and we call this the codomain. So there's unique 1-to-1 correspondence, right? You don't have, like, if we have a function that takes 1 point and assigns it, oh, it keeps dying. The pen, it's so annoying. So if we have a function that takes one element of A and assigns it to 2 elements of B, it's not an injective function, since there's no longer a 1-to-1 correspondence here, because this one element of A is being assigned to 2 elements of B. We only want one element to get assigned to one other element for the function exists. Okay, so this would be an injective function, but if one element gets assigned to 2 elements, it's no longer an injective function. However, this would still be an injective function, since it's the same point being mapped onto the other point. So how does this definition capture what I just described? Well, it's saying that, so f of x, so x is just like some member of A. So f of xn, so you're taking some point xn, and you're mapping, and the function will map it to some point on B. Okay, so I take some point and I map it to B. If I have another point that maps it onto the same element, that would mean that the functions are equal, and that would imply that xn has to be equal to xm. So that would mean that these points would have to be the same point. So this is not an injective function, since these points are equal to each other. However, if I have this mapping to this point, and then I have another point that maps to the same point, if xn equals xm, which is just the same point, so this point does equal to the point, it would be injective. So that's how it captures what we've described. Now, if you don't know what I mean by x and xm, like here I have A has, like, say, elements A, B, C, and so on. This would be x1, this would be x2, this would be x3, and I use xn and xm to be like the general number. So we're saying that if f of xn equals f of xm, which means that we take one point, map it to another point, and we just take some other points, which could include the same point as originally, and it maps to the same point. And plus, those 2 points, those 2 members of the domain are the same point. So that's how it beautifully captures what we've described above. And we can use this definition, this rigorous mathematical definition, to prove whether functions are injective or not. So, for example, so you have f of x equals e to the x. Is e to the x injective? Is it injective? Well, if f of xn equals f of xm implies x equals n. Xn equals xm, and then it's injective. So what we do is we take, okay, so f of xn should equal f of xm, which is just e to the xn equals e to the xm. We can take natural log of both sides, and we get xn equals xm. So this function does, so if f of xn equals f equals f of xm does imply that xn equals xm. So it is injective. That's how you'd prove it. So this is why this definition is so beautiful. It may seem a bit aberrant or abstract, but it does very beautifully, very well, perfectly capture, did I say very well? Very well, perfectly capture one-to-one correspondence. And we can use this to rigorously prove whether functions are injective or not. So what about surjective functions? Well, a surjective function is a function that maps all elements of the domain, which would be like A, right? To some elements. Okay, to some elements of the codomain. Now, it could be all elements. It could be some or all. There's freedom there. But if a function maps all elements of the domain to some elements of the codomain, it's a surjective function. So let's go back to this image, this picture here. Okay. So here I have some function. Okay, it assigns this to this, this to this, this to this, this to this, and this one point to the same point. So to another point. Okay? This function is not surjective. It is not surjective. Because there are some elements of the domain that don't have any map. The function isn't defined for those points. However, if we did define the function for those points that maps like this point, say this point, and this to this point, and this to this point, then it would be a surjective function. Since it maps all elements of the domain, none is left behind to some element of the codomain. And note that one, it doesn't have to map it to all of the elements, but as long as some of the elements are mapped to, it's a surjective function. Now note that this is not injective, right? Because I took some 2 points and assigned it to the same point. For example, this one point right over here, to these 2 points, these ones were mapped to the same point, so it's no longer injective, but it is surjective. Okay, here's a bit of a more nicer example that's not so rude and mean. This, for example, and this gets mapped to this here. Actually, let me just erase some points to start with to make this example a bit more nicer. So I have this maps to this gets mapped to this, this gets mapped to this gets mapped to this one, and this gets mapped to this. Let's just erase this point. This is still a surjective function, so this one is surjective. Because all the elements of the domain get mapped to some of the elements of the codomain. In this case, it's actually all the elements of the codomain. And note that this surjective function is also injective too, since there's a unique one-to-one correspondence of the elements of the domain to the elements of the codomain once the function is defined. And this brings us to what bijective means. A bijective function is just a function that's injective and surjective. Oops. Pen died once more. And surjective. In this example I gave right here, it's injective and surjective, so it is bijective. So it's also bijective. Yeah, those are all what they mean. All those words mean. They're not very complicated. So yeah, that brings us to the end of this video. This was a nice intro to set theory. Hope you guys enjoyed that. So if you guys have any questions, please leave them in the comments. Please consider sharing if this did help you. And yeah, have an amazing day. Bye.